Okay, so good morning. Yeah, so I hope you like the exam. Okay. We will see. We will see. Okay. So today we will continue the discussion on linear recurrence, and then all of these are with constant coefficients, and then we will talk about more on how to get a homogeneous solution, and then after that, let's do some examples. Let me close the door. Okay. So we have talked about. So let's take a look. Okay. Of this example. So let's say an. Let's say we have something like an is equal to an minus 1 plus an minus 2. So for this one, if we want to get a homogeneous, so a particular solution for this one will be very simple. 0 will be a particular solution because 0 is equal to 0 plus 0. Okay. And for homogeneous solution, how do we get it? So last time we have talked about we can first get a characteristic equation of this one. So maybe this is going to be x squared is equal to x plus 1. This will be the characteristic equation corresponding to this one. And then let's say we get the roots. So let's say x will have roots like alpha and then beta. Okay. And then for this example, the two roots are different. Okay, so we will see that the homogeneous solution for this characteristic equation will look like this form. It will be some constant a times alpha to the power n plus some constant b times beta to the power n. Is that okay? Okay, and now if we have the initial condition given, for instance, let's say I tell you what is a0. Let's say a0 is equal to 1, and then let's say a1 is equal to 1. Then we can plug in a0 and a1 into this formula and solve for the unknowns of a and b. Is that okay? Alpha and beta, they are all known. These are constants, you know. The only thing is we don't know this a and this b. This a and this b will depend on the initial values of a0 and a1. Is that okay? So this example is exactly the recurrence for the Fibonacci number. And then by using this, we will be able to find out what is A and what is B, and then in overall, we get the solution. Okay? Now, this is the case where we have distinct roots. And it turns out that this is a degree 2 polynomial, which has 2 distinct roots in this example. And then the initial condition, the boundary cases, there are exactly 2 of them. So 2 boundary cases, 2 distinct roots, 2 variables here means that these have sufficient information for us to solve for this A and this B. And so this homogeneous solution will be the unique solution for solving the whole problem. But let's look at a different example. This time, let's look at another case. So for this one, let's say an minus what? Minus 4 an minus 1 plus 4 an minus 2. Let's say this time is equal to 0. Now this is also a degree 2 recurrence. So if I fix the value of, let's say a0 is equal to what? Let's say a0 is equal to 1 and a1, let's say it is equal to 2, then we will be able to compute what is a3, and then what is a4, and then what is a5. But if you look at this characteristic equation, then we will see that this will be x squared minus 4x plus 4 is equal to 0. Okay? So that x will be equal to what? X will be equal to 2, and this 2 is a repeated root. So it is repeated root. So if I am saying that, okay, this an will be, let's say if we are using our example, let's say this is going to be a times 2 to the power n plus b times 2 to the power n, then this doesn't make sense. Because you can combine this a and b together into a new constant, let's say a plus b, which is equal to c. So that this has only degree 1 freedom. But then in the end, your thing has degree 2 freedom. So this doesn't match. So this is not the correct answer. This is not the correct answer that describes all the possible solutions for this one. Now, what could be a possible solution? So let's look at this case. So previously, we know that, let's say this, let me just in general, let's call it alpha. It turns out that alpha is equal to 2 in this case. Previously, what we know that alpha to the power n is a possible root for this thing. So we know that alpha to the power n minus 4 times alpha to the power n minus 1 plus 4 times alpha to the power n minus 2 will be equal to 0. This is what we know. Okay? Now, the interesting thing about a repeated root is that if you differentiate the equation once, it will still be a root. Right? This is repeated root. And if a root, the multiplicity of a root is 3 times, so it is like x minus 2 times x minus 2 times x minus 2, then if you differentiate it 1 time and again 2 times, it is still a root. Is that okay? Okay, and for our example, it is just a repeated root with multiplicity 2. So you differentiate it 1 time, it is still a root. So what does it mean? So if I differentiate this, so this time let's use differentiation. Differentiate this, what do we get? With respect to this root, let's imagine this is x, this is x, this is x. And then you plug in alpha there, then you will have n times alpha to the power n minus 1 minus n minus 1 times alpha to the power n minus 2 plus, sorry, there is a 4 here. I missed that. Minus 4 plus 4 times n minus 2 times alpha to the power n minus 2. It is equal to 0 in this case. So if alpha is a repeated root. Is that okay? So what does that mean? Let's take a look. So if I set an to be something like n times alpha to the power n minus 1, then this will become an. This will become what? This is an, right? This is the same as this one, right? And what is this? This is an minus 1, right? And what is this? This is an minus 2. So if I set an to be something like this, then it implies what? It implies an minus 4 an minus 1 plus 4 an minus 2, it is equal to 0. This is what we want. Okay? Is that okay? Is that okay? And in fact, if I multiply this with b, as some constant b, then we will still have b. So if I multiply this with b, then we will see that b and a times. So I multiply everything by b. So we have 4b here and then 4b here. I multiply everything by b. Then this will become 0, right? And then we will still have an minus 4 times an minus 1 plus 4 times an minus 2. It is equal to 0. Okay? So if something is a repeated root, if alpha is a repeated root, not only we can write down a times alpha to the power n, we can also write down b times n times alpha to the power n minus 1. It's a solution. Does that make sense to you? Okay, so this is it. So you can, so in that case, if you take a look, this has 2 initial conditions, 2 boundary conditions, and then we have 2 unknowns. Okay? And these 2 unknowns, you cannot combine them because one you need to multiply with n, and then the other one you don't need to multiply with n. So these 2 represent different things. So in that case, if you solve for what is a and what is b, then you get the solution of the whole thing. If you are okay with this, could you please raise your hand? Okay, good. Now, This may not look nice. This may not look nice because you have alpha to the power n here, alpha to the power n minus 1 here, right? Okay, why don't we just set? Okay, so let's try to divide b by alpha. So let's imagine we have some new constant. Let's say b prime, which is equal to b over alpha. Alpha is a constant. B turns out to be a constant in the end. So you can have something called b prime, which is going to be a constant. Then you can write this down as a times alpha to the power n plus b prime n times alpha to the power n. Is that okay? So in that sense, the general solution is actually looking like you have alpha n here, and then because it is repeated 2 times, you have something like a plus bn here to multiply with it. Okay? Is that okay? Is that okay? Let's solve for a problem and see if it works for us well. Okay? Okay. Let's try to look at this matrix. Okay. This matrix is like 2, 1, and then a bunch of zeros. And then the next row is 1, 2, 1, and then a bunch of zeros. Zeros, and then the next one is going to be 0, 1, 2, 1, 0, 0. You have 0. You have 1, you have 2, 1, and then in the end, it is going to be 2, 1 again. No, in the end, let's say this is 2, 1, and that is 2, 1, 2, 1, 2, 1, 2. Okay. Imagine we have a matrix like this. These parts are all zeros. Okay, maybe I'll just write down these zeros here, you know. Zeros, 0. So these are zeros, these are zeros. Okay, can you imagine how it looks like? So it is a square matrix. So you have a diagonal, all 2s, and then on this side, the next diagonal is all 1s, and then on that side, it is all 1s. Is that okay? So this is the matrix. And then, let's see. Yeah, I just want to double check if I'm making any mistakes. Okay, good. And then let's say that it is an n by n matrix. So the n here, and then n here. Okay. So what I'm interested is I want to get the determinant of this one. Determinant. And let me call this determinant an. And we want to find out what is the value of an. So let's do a simple thing first. What is a1? a1 is just 1 by 1, right? So a1 turns out to be equal to 2. So it is equal to 2. Is that okay? And then what is a2? a2 is going to be, you look at 2 by 2. So it is like 2, 1, 1, 2. Is that okay? So 2 by 2, I know how to get the determinant. So I multiply this row, this diagonal, and then minus this diagonal. So this will be equal to 3. Is that okay? Let's also do one thing, a3. a3 is equal to what? a3 is equal to 2, 1, 0, 1, 2, 1, and then 0, 1, 2. I want to get this. Is that okay? 3 by 3, we can still use this diagonal method. So I want to sum up this 2 to 2, 1, 1, 0, 0, 1, 1. This direction is add. This direction is subtract. Okay. So this will be equal to what? This will be equal to 2, 2, 2. So it is 8, and then 0, 0. Is that okay? Minus what? Minus this 1, 1, 2. So minus 2, minus 0, 2, 0, minus 0, and then minus 1, 1, 2. So minus 2. So it is equal to 4. Is that okay? Okay. In general, how do we compute the determinant? So in general, to compute the determinant, it is like you can fix a certain row or you can fix a certain column. Any row, any column will be fine. Let's say we fix this row. So we want to compute the determinant of this one. It is going to be 2 multiplied with the determinant of this part. Is that okay? Minus 1 multiply the determinant of this part with this remaining column part removing. Is that okay? And then plus this one multiply with the determinant of this part with this one removing. Is that okay? And then so on and so forth. Now for our case, it is good. We have 2, 1, and then all the terms here will be equal to 0. Is that okay? So what do we know? So in general, for this case, for this AN, yeah, we can have a very nice thing observed. So we can have this nice thing observed. It is going to be, so AN is going to be equal to 2 times what? Times that part, removing the first row and first column. So can we? So what will happen if I remove the first column and first row? It will be AN minus 1, right? Is that okay? So AN turns out to be equal to 2 times AN minus 1. Is that okay? And then we still minus. Minus what? Minus 1 times this thing times this thing. This thing looks like 1, 0, 0, dot, 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 0. And then this column removed. So we get what? We get 1, 2, 1. 0. 0. Is that okay? And then 0, 1, 2, 1, 0, 0. Is that okay? So we get 1 here, we get 2 here. No, the last one. So this is the last one. 1, 2, 1. Oh, 1. Eh? No, we still get 1 up to the end. Yes. We have a 1 here. We get this 1 here, and then all of these are 0. Is that okay? So it is minus 1 times what? Times as if the row corresponding to this 1 is removed and the column corresponding to this one is removed. So we remove the t and pack the remaining together. Is that okay? And what is it? What is it? This is going to be what? This time let's fix the column. Because the column has just 1, 1. If you look at this column, it's just 1 times this 1. And nothing else. And what is this part? AN minus 2, right? Right? Good. So this is equal to 2 times AN minus 1 minus AN minus 2. Is that okay? What is the characteristic equation? The characteristic equation will be what? Will be x squared is equal to 2x minus 1, right? What is the root? 1. Repeated root. So what do we know? So particular solution for this one is still 0. So the total solution will be looking like AN. It must look like something like, using our method, it is going to be A of this form, A plus BN times the roots to the power n. Is that okay? Is that okay? So it is going to be a plus bn. Okay? Is that okay? Now, let's use a1 and a2 to help us to get out. You don't need a3. You just need two cases. You need two boundary conditions to solve for this a and b. So a1, we know a1 is equal to what? We know a1 is equal to 2. 2 can be obtained by putting 1 into this formula. Am I correct? So 2 is going to be a plus b. So if we are using a1 is equal to 2 to help us. Okay? Now, what do we have? We have a2 is equal to 3. So we have 3 is equal to, you are using 2 as in the n. So a plus 2b. And then here we are using this a2 is equal to 3 to help us to get this one. You solve this. This is, so you this one minus this one, you get b left. B is equal to 1. Is that okay? Now when b is equal to 1, a is equal to 1. Good. So an is equal to, after solving this a and b, a will be 1, b will be 1. So this will be n plus 1. Is that okay? And it works. Look at it. A3, it turns out that it is equal to 4. So it works. Okay? A5, 6. A100, 101. Is that okay? Okay, good. Now test your understanding. So let's test your understanding.